Oindri is a commie. The stream is way too educational. Um, okay. Strongly interactive. Strongly interactive ones are called simps. So, you mentioned, Reese, I think, mentioned WIMPs, weakly interacting massive particles. WIMPs are actually a candidate for dark matter. But it's good that you bring this up as we talk about particles, and I think I was just now mentioning neutrinos. The stream is good. She makes it food. Yes, if you think of all of this as food, then I think we're all good. So weakly interacting massive particle is a candidate for dark matter. Why am I saying candidate? Because dark matter is not confirmed. We don't know confirmed like what dark matter is, but we can imagine and think things and hypothesize and try to find such a candidate that we have thought up with various experiments and things like that. WIMP is one of them. So weakly interacting massive particle. Now, the first candidate that people thought of when it came to dark matter was actually neutrinos. So this neutrino particle that I just mentioned is, yes, neutrino is a candidate. Neutrino was a candidate for dark matter as well. Why? Because neutrinos are very, very elusive. So I was just now mentioning certain boson examples, W and Z bosons. Those are the carriers of the weak force. Turns out that neutrinos are particles, they are types of leptons that only interact through the weak force. They don't interact through photons. And they, of course, interact also with gravitation because they have a mass, but it's very low. So for a while, people actually thought that neutrinos might be massless. That's how low mass they are. But because they're so elusive and they don't interact with photons, same as dark matter, you can't see dark matter because dark matter is not interacting with photons. But it is interacting with gravitation. We know that there's this extra matter. It affects gravity, but it does not show itself with light. It does not have a luminosity. So we thought, as a candidate, that maybe neutrinos could explain dark matter. Because what is dark matter? It is a question mark, right? It's a question we have about this extra matter, this invisible matter that we know not what it is. And we're thinking, maybe it's neutrinos. So that was a candidate. But the problem was that the neutrinos were too low mass. Because neutrinos were too low mass, they could not explain dark matter appropriately. And that helped us to come up with a new type of particle. Imagine in our brains a new type of particle. So I want to be very specific what I mean here, right? It's a thought, it's a hypothesis, which is the WIMP, which is what somebody mentioned, which is basically WIMP is exactly like neutrinos, but more massive. Because you can imagine a more massive particle that's kind of like the neutrino, right? If you're, say, looking for one, why not? So that's the WIMP, weakly interacting massive particle. I don't know about SIMP, strongly interacting massive particle, because the strong force is different. The strong force is between the quarks. Actually, the strong force is within the nucleus of the atom. Remember we talked about neutron degeneracy pressure in the context of neutron stars? That particular, so neutron stars are maintained by neutron degeneracy pressure. The force between the subatomic particles are, as in the subnuclear particles, are is actually the strong force. Neutrinos interact through the weak force. Electrons also interact through the weak force. The uniqueness of neutrinos is that they only interact with the weak force. If the neutrinos also interacted with photons, then they would be less elusive, but they don't. Similar thing with dark matter. We see it to not interact with photons. So we're thinking it might be kind of like the neutrino in that sense, but we would want more mass. We would need more mass. And so we thought up the WIMP. But that was a little bit of a tidbit on particles. Hopefully you enjoyed that. And if